Welcome back. In this learning module, we're going to be learning about looping structures in C, while loops, dual while loops, and for loops, and learn a little bit more about coding practice along the way. Our understanding so far is that we've seen the need to do more than just calculation in computers, so we've certainly had to do things that are data dependent. That was our motivation for understanding the if statements, if else, the switch, as well as the more complex versions of the same, to allow us to do data dependent decisions. One of the examples we worked on last week was essentially sorting five numbers using just if statements. This is a visualization a little bit better than the hand drawn one. We took a pass through bubble sort. We compared 1 versus 2, var1 versus var2, 2 versus 3, etc. And then we had to actually repeat that process a number of times to get a fully sorted result. As a motivating question for this learning module, I want you to think about this example with five numbers. Do we really need a computer to sort just five numbers? Probably not. That much we can do by hand. But what if we had 5 million numbers? Does the basic task really change significantly? If we only were using the code template we worked on last week, that would be quite cumbersome. Work for five numbers, we could probably do six, we could do 15, something like that. For 5 million numbers, that would be a very challenging piece of code to write and to make sure there weren't any bugs in it. So, just like computers, we think of them as being very good at decision making. Computers are also very good and really originally invented to automate tasks that were either too time intensive or potentially error prone to do by hand. Most programs have these control and data flow graphs that don't just have the branches that we've learned, but also repeat operations a finite number of times depending on some condition. And that's how we visualize this in the graph here on the left on this slide. We have some variable assignments that are happening. We have our conditions that are some if, else, some Boolean operators, and then given some sort of condition, we decide to repeat that whole process a certain number of times again. And so that's our introduction to repetition structures or looping structure. Just a way that allows the programmer to specify some functionality that can be repeated multiple times. Repetition, otherwise just known as loops, the same term in computing. The while loops in C are the simplest version, and all of our loops have three main components, and I want you to remember these three components. There needs to be some expression that initializes a variable that allows us to control the loop, so-called loop control variable. It's going to be A in the example on this slide. There needs to be some loop repetition relational operator. Just like with our if statements, and it's not a coincidence, our syntax looks quite a bit like an if statement here. We have our a less than 3 relational operator. And then inside the loop, there needs to be, for that third thing, some expression that is going to update the loop control variable. So we go from a condition that keeps us in the loop to eventually some condition that gets us to leave the loop. So in this example, a is the loop control variable. If a is less than 3, then we loop over using the while structure. And finally, at some point inside the loop, we need to update that a loop control variable within that loop to have some reason to actually exit the loop. As I mentioned, the syntax of the while loop is purposefully very similar to that of the if statement we saw in the previous learning module. If some statement is true, then do something is very directly analogous to while some condition or some value is true, then do something. If is for a single decision our code needs to make. While implies that there's repetition within our code. So what does this program do? We can walk through the code. Of course, it's code. We have the advantage of being able to directly run it. But let's walk through it first. We have a variable input, another one sum that is initialized to 0. That strongly implies we're storing some summation of something here. While the sum is less than 0, and it certainly starts off less than 0, printf, our print scan prompt here of enter in an integer, read in an integer, and then take the value of sum as currently stored and add the value of that inputted variable. So this is a running sum. We're going to keep inputting integers until eventually the sum of all those integers is greater than or equal to 100. If it never gets greater than or equal to 100, we'll stay within this loop. I think we get it, but let's actually just run this code briefly. Enter an integer, 7. This is maybe our first time having our print scan prompt repeated here in a loop. There could be valid reasons to do that. We enter in things until we no longer want to enter any things. That's 7. Let's do 10. That's 17. That's 37. That's 47, and 37 plus 40 is 77. Then plus, let's say, add another 30. That should get us to our sum of 107. We can see we were going to continue within that loop forever until we got to a sum that was greater than 100. So if we were doing this, it would take a very long time to eventually get out of the loop, but we could do so via um, adding up to a value that's greater than 100. So that's our basic while loop. We are executing the body of that loop until this condition is no longer true. So it's repetition. We're repeating the if statement over and over again. And for that reason, we need to have a variable for our relational operator. We need to have that relation, that actual check, whether the condition is still true. And for this loop to eventually terminate, we have to have some expression that's going to update that loop variable. So I think we figured it out. We could see what that code was going to do. How about this version of the code? Not that different, although we're not prompting for a value here. We have an int a, we initialize to 1. We also have a summation. While a is not equal to 20, we increment our sum via the value of a. So sum is, we should probably initialize sum here for it to be correct. Sum would be 0, then sum plus 1 is our new value of sum. And then we're also incrementing a by 2 each time. So a was 1, a was 3, a was 5. When we get out of that loop, we finally print out sum is the value of sum that we have here. The hints are pretty strong what this code is doing and why I say be careful with loop. We have our MC Escher crazy stairs drawing here. We have the warning to be careful, and if you need an additional hint, we have the name of this REPL here, which is infinite loop. Well, what's going to happen? We're going to hit run, and we're going to wait, and we're never going to get out of that loop. It is an infinite loop. Not that hard to do. You may look at this example and say, well, I would never create an infinite loop in my own code, but it's very easy to inadvertently construct a loop that actually never reaches that exit condition. That's what's known as an infinite loop, and it can be pretty difficult to debug. Yes, if it's just a straight piece of code that has an infinite loop, you would be able to catch that. But if it's some edge case for which only a certain set of conditions are the case that would cause your infinite loop to be true, that can be quite more difficult to debug. Sometimes we don't actually want the loop to end. If we were writing a control loop for an embedded system in our C code and we want to be just constantly monitoring data and performing some calculations on it from the time the system powers on till the time the system powers off, then a while loop might make sense that is infinite in nature, a so-called infinite loop. We actually never want that loop to terminate. We don't want the program to ever exit. For the programs at least that we are writing this semester, and for most of the programs you would write in most contexts, we would want to keep the loop going until there's some reason for that loop to exit. So we have to be a little bit careful with our logic. There isn't necessarily a fix for this infinite loop because we don't have a specification for what it's supposed to do. Perhaps if instead we checked while a is greater than or equal to 20, then it would at least stop once a got to that point of being 21. It would never actually reach the value of 20 here. A small aside, we've been having these assignment statements quite commonly that are updating a variable's value. They're extremely common. From the previous example, we had a equals a plus 2. C actually provides a set of what's referred to as compound assignment operators that does simplify the logic. Simple is in the eye of the beholder here, but it requires fewer typing of characters to actually update that variable. If I know it's a that I'm going to set as the result of incrementing a itself by 2, instead of writing a equals a plus 2, we can write a plus equals 2. Same for subtraction, multiplication. Really, for any operation we have defined, we can, instead of variable equals variable op, we can write variable op equal expression, and it will give you the updated version of that variable there. It's never strictly necessary. The extent to which it actually simplifies things is potentially debatable, but we can certainly do, instead of a equals a plus 2 in this code, we could write a plus equals 2. Doesn't actually change our infinite loop here. Is this simpler, easier to read than the other example? It's hard to say, but it's a very common thing you'll see in C code, so being aware of it is an important thing, I believe. Much like our if statements, where when we're having them in our code, we have to really think about what are the branching conditions, what are the different paths my code should take to generate a result here. Loops really need to become part of your problem solving process. So you have some program you need to write. As part of that problem solving process, you need to ask yourself, is there any repetition? Am I doing something a certain number of times in my code? Usually the answer is yes. For interesting programs, we're doing things multiple times. A secondary question is, do I know in advance how many times I'll be looping? If we're using while loops, we don't necessarily know in advance how many times we're going to loop. If we do know how many times we're going to loop, we should use a for loop, as we'll cover here. And then the third question, as it relates to the structure of our while loops or for loops, is how will I know when I need to stop looping? Got to be based on some variable's value, but what that is, that's what you have to decide as you're writing your programs and as you're solving the problems. Oftentimes in our while loops, we'll set up what's referred to as sort of a sentinel value that is there specifically to get us out of the loop. And it would have a name something like keep going in loop. You would initialize it to 1. It's not actually directly related to the math that your code is implementing. It's literally there just to let the while loop know it's time to leave. So keep going in loop, initialize to 1. Every time through the loop, we're checking that sentinel value that it's equal to 1. And when some condition, it could be a very simple, it could be a more complex condition, is then true, we then set that keep going in loop sentinel variable to 0, go back to the loop. That's when we would finally get out of our while loop. It's not required, it's just a very common design pattern. Let's try a problem solving exercise. This is not a straightforward one. Maybe we'll make part of the progress and then continue the second half of this in the next video here. This is also a very well known programming problem, so there's nothing necessarily new to you here, but it'd be calculating the values of the Fibonacci sequence. Our input would be an unsigned integer, in this case representing a maximum value, and our output isn't all the terms of the Fibonacci sequence, which as debugging steps maybe we would want to do, but it would be the sum of all the even value terms in the Fibonacci sequence that are less than that maximum value. The definition of the Fibonacci sequence is we initialize with 1 and 1, or 1 and 2. Either way is fine for our purposes. We initialize and we start with those two terms, and we generate the next value in the sequence by adding the previous two values. So we take 1 plus 1 and get 2, then 1 and 2 and get 3, then 2 and 3 and get 5, and so on. It grows fairly quickly. For our purposes, we're going to set a maximum value, and we're going to want to add all of the even value terms in that sequence that are less than a maximum value. So we have the problem, and we know that the first thing we do is we get to our code and we get writing. Wait, no, we know that's not correct. We don't necessarily get writing right away. It's good to have our comments and our spec listed here. That can be pretty useful. Let's go to the whiteboard. Let's take a look at what the problem solution would need to look like and where a loop may or may not be helpful for that. So we have our values that we know we're going to want to generate here. Our 1, 1, 2 values as part of it. Whether we start with 1 and 1 or 1 and 2 doesn't really matter, but it doesn't matter in fact for this purpose. But we know that we're going to do 1 and 1, or 1 and 2 is our first two values here. Make sure we have some way of referring to them in our code. We know when we see it, hey, yeah, that's a 1, that's the first term, that's another 1, that's the next term. We have to be a little bit careful here with how we name these. We've been using var1 and var2, and I think that's going to get pretty ambiguous quickly here. Let's think of this as like the previous term in the sequence. It's not the current one. This one being the current term in our sequence. We will have to then add them together. That would then be called the next term in the sequence. I mean, var1, var2, var3 is also fine, but it doesn't connect to anything we're doing as part of the problem solving here. Spec was we have to check the values that we're generating in the sequence, and if they are even, then we should be adding them to a sum. So somewhere there is a sum variable. We also have to define that somewhere. And we have to be checking these values as we're generating them. Checking if they're even. Do we remember how to check if something is even? It involves that modulo operator. And then we just repeat. We just loop through and we continue doing this until when? Until the value we're generating is less than some input maximum value. If it's not, we keep going Otherwise, we probably need to like print out the max value, but we're done in that case. Usually when doing the problem solving process, I like to think about data, and I like to think about the relationship between the variables in my code. I have to think about some of the decisions my code will have to do. I don't draw it out as thoroughly as some of those control and data flow graphs that we had on some of the prior slides in this and the previous learning module. That's pretty cumbersome. Some situations and scenarios may require you have that low level of detail in your specification for the problem. I think that's a bit much. I mean, here we could say this is the false path and this is the true path. So, um, except if we did that, we'd be wrong. This would be the true path of we're less than the max value. This would be the false path. False path. We are no longer less than the maximum value, and that kind of shows sufficient things for this is our iteration. This is our while loop structure. Keep going while that's the case. Didn't even quite draw this as a branch here, but it would be a branch here if even add the sum. But either way, keep doing that check. What this finally then doesn't show, which is a little different for this problem maybe than a couple of other programs you've already worked on, is we have the previous value, we have the current value. We know how to calculate now the next value, but then we have to kind of shift things along, right? 1 plus 1, this is our current value. We know the next value is there. We then have to kind of move things along, and what was current is now next. What was previous, the arrows would actually go in the opposite direction. What was our next value is now our current value. What was our current value is now our previous value, and we don't actually care about our previous value anymore. So we would probably want to still use the same three variable names, um, but we have to kind of shift them. It's kind of similar to the swap operation for our bubble sort from LM-03, but it's not exactly swapping. It's just kind of shifting things around. We probably don't need a temporary variable for that, but we may have to get the order of that shifting correct for this to actually work properly. Let's open it up again now that we have the understanding of the code and our spec here. Let's think a little bit about the variables. So we're not printing hello world, but there's some sort of prompt. So enter in a max value. Again, you should be getting almost like muscle memory of these kind of print prompts and scan prompts here. We call that max val in our brief spec. So we know we'll need a max val. For now, that's probably sufficient. And then we'll talk about why this is valid in terms of the coding rules of C. We can actually declare our variables. They don't have to go at the very beginning of our program or of our function. Can be good practice. I can move these up ahead. It would also be fine. But max val, we've read it. Here it is. These variables now have to do with the Fibonacci sequence, and we have our while loop. While our current value is less than max val, we should be doing the thing. We should be generating the next value. Is the current value even? That was our thing we're interested in. If so, add to sum. So to check if our current value is even, we do that mod2 operator. You can do mod2 equal to 1, and that's fine. There's nothing wrong with doing that at all, except it would be 0. If mod2 is equal to 0, is the correct thing here. If it's even, mod2 would return 0. If it's odd, mod2, the remainder when divided by 2 would return 1. If so, we have our sum. Now we have our fancy compound statement. Sum plus equals current, right? We've taken the value of sum, we're adding it to itself plus that value of current. We're updating the value of sum. Then we have to calculate the next value in the Fibonacci sequence. And it's just the sum of the previous two values. Then it gets a little tricky, I would say, here in that we have to shift those things along here. So we have the next value we've just calculated, shift cur and previous. What was previous is, or what was current is now previous, and what we care about, the current value we're interested in, is what we declared as that next. And then, of course, once we've gotten a current value that's greater than or equal to max value, we can print it out. Sum of even Fibonacci numbers less than, let's add that to the prompt, less than the max val is our sum. Not a lot of debugging statements along the way. Certainly, I'd probably want to print out next to confirm that we're actually generating it correctly. Let's enter in a next value of thinking about our Fibonacci sequence here, we're adding even values to it. So let's check 10. Well, 10's funny. How about 14? So what is the sum of even Fibonacci values less than 14? The result should be 10. My prompt got a little messed up. I didn't really need to do a new line before we entered value. It's still correct, but it's not what we normally do. Sum of the even Fibonacci numbers less than 14 is 10. We have a little bit of a verification problem here, right? We've written code, but if I type 2048 and it says the sum of even Fibonacci numbers less than 2048 is 798, is that correct? um, that's a different programming problem than the ones you're facing. I provide you test cases, and I will tell you if your code is sufficiently correct. We probably have to just work with smaller things here. We saw that 34 was the next even Fibonacci number. So let's check the sum for numbers that are less than 40. So that should be 2 plus 8 plus 34, and we should get a result of 44. If we really are worried about that, we can check what's the next even Fibonacci number. It's going to be 144. So let's check the max value of 150. It should be 44 plus 144, 188. Okay, we didn't thoroughly test our code, but it seems okay. Back to our repetition structures. Another kind of companion one to the while loop is referred to as a do while loop or just a do loop. It's very similar to the standard while loop. The main difference is, as the name kind of implies, it's we do first, then we check whether the while condition. So it's a little bit inverted, where the regular while loop is we check the condition, then we go inside the loop body here. So that's the main difference. The loop body is executed first before conditions are checked. That can be useful if you have a piece of code that you know it's going to execute at least once. That no matter what is the case, we're at least doing something once. We may do it multiple times, but we're going to do it at least once. Our regular while loops may not execute at all. If current value or max value was set to 0, that Fibonacci loop wouldn't have executed at all. So for our do while loop, it would be, we know it's going to do it at least once. This may be a good choice for that. Syntax is a little weird, and if you get it wrong the first time, that's fine. There's the word do, which is in the curly braces, and then the while condition is outside those curly braces with kind of a semicolon on its own. But syntactically, it does what I think you would expect of it. Do something, then check the condition. If the condition is true, then it kind of becomes a while loop at that point, right? Where we're going to continue looping through. We basically do something n plus 1 times for n checks of our while conditions. So we're guaranteed, even if the condition is instantaneously false, we've still executed that loop once. Could be useful for our entering in a certain number of numbers looping example, where if we knew that we wanted to grab the value at least once and make sure that it's greater than 0, then we want to have at least one prompt. Then a do while loop might make sense. We don't use a lot of them this semester. There's nothing wrong with them, but we can get a lot done with our while, and as we'll see, our for loops. A small aside about using floating point, which we don't do a ton of, at least early on in the semester here, with our loops. Slightly less of an issue with if statements, but it would also be a bug with our if statements. We have floating point representation, either our regular floats or our double precision floats. There's still finite representation. There's still a finite number of bits to represent kind of an infinite space of floating point numbers. So our result is less likely to be equal to something else. This can lead to incorrect results in infinite loops. This code here itself isn't necessarily that important. It's a Taylor series expansion to calculate Euler's constant or e to the 1 at least. And it's going to keep doing the Taylor series expansion. Again, the details aren't that important, but it's going to keep doing the Taylor series expansion until the estimate is then equal to what we believe to be a correct value for e. So calculate, and the math is actually correct for whatever that's worth. We're doing factorial and we're adding it, the inverse of it. So we're dividing by the denominator. We're then calculating the new factorial value, and we're calculating maybe how many times it takes to get a value that's equal to this predefined value that we have here. Be a piece of code that checks that the series expansion actually works as intended. The problem with it, though, is we're doing an equal comparison or a not equal comparison, and we have to be a little bit careful to have a result that will actually reach that exact value. Doesn't really show much. It's just showing an infinite loop because while the math is correct, we could add a printf here. Let's just add the same printf that's already there. By the way, if you're running code and you're stuck in an infinite loop, that stop button should work. If it doesn't, Control C or Command C, depending on your system, will also get rid of and end that code for you. It happens to all of us, so um, don't feel guilty if you have an infinite loop in your code. You have to manually kill it. Happens to everyone. But we'll see here. Takes a few terms, and then things go haywire. So the solution, such as it is for a problem like this, is to, for floating point values, is actually not to usually do strict comparisons where we're doing equal versus not equal, but instead, and this is something we haven't really covered, so I don't expect you to just know this already, is to check if the value that you're calculating is actually sufficiently close to the value you're interested in. In this case, because I don't actually know if we're going to be less than the estimate or greater than the estimate, one approach, if you're not sure if it's less than or greater but close, is to take the absolute value first. Take the absolute value of the difference between what we are calculating and what we're expecting, and then this is a very common thing in floating point code sets in our do while loop here. If the estimate minus the value, the absolute value of that, is within some tolerance, and I actually don't know what the right tolerance should be, but we'll try 0.001. And as we run that code, start with an estimate of 1. The estimate is increasingly getting closer and closer. I don't know what tolerance is going to cause this to go back to being a infinite loop here. It looks like we can hit 0001. Can we hit 00001? Yeah, it only takes a couple more terms to get a very accurate estimate using that approach. I think the main takeaway is if you're working with floating point, you should be able to do relative comparisons, less than, greater than. Just be careful when doing equality because that can lead to infinite loops that you wouldn't normally expect. Switching gears a little bit, but now I want to talk about for loops here. Remember those three main components that are found in our loops. An expression that initializes a loop control variable. Some relational operator for loop repetition, while something. That something is our relational operator. And then something inside the loop that updates the loop control variable so we have a way to get out of the loop eventually. The for loop in C syntax is only there to allow us a way to explicitly list all three components, and the syntax for it is as follows. For is the keyword, some initialization of a variable, some condition we're always going to check, and some update of that loop control variable. And then inside the brackets of the for loop is the thing we're doing inside that loop. Maybe you've seen this before in other programming languages or in prior courses, but this is why we have the for loop. It's the same as the while loop. It's just a very explicit way of listing the three components of our loop. And it's very clear what the code is doing by looking at the for loop there. There's no reason it had to be in this order, but that and many languages are in this order. Variable for the loop, initialization. Thing we check in the beginning, because it's a while loop, not a do while equivalent. We check in the beginning and we check every time we've gotten through the loop body and what we should do when we've gotten through the loop body. We initialize I to 0. We check every time that I is less than 25. And then we increment I by 1 to go to the next time through the loop. When do we choose a for loop versus a while loop? I think the correct shorthand is when we know there's a bounded number of iterations, that I have code I know is going to run 25 times. And even if that is n, like so I know the code is going to run a variable number of times where I know the variable or can have the variable at runtime in my code. For loops make a lot of sense. The code's just a little bit cleaner, less places to screw it up really. So we have, as part of the loop, we have to define our loop control variable. We already had to do that before, but here it's more explicit. Also more explicit in our for loops is oftentimes we have these loop control variables. We don't really care about the variable itself that much, and so that's why you see it named I, J, and K and things like that. Maybe that's not great practice, but that's modern practice. That it's a loop iterator variable. It's index, so I. And if I need a second one later on, that's J. And if I need a third one, that's K. If you start to use L, M, N, O, P, maybe it's time to rethink your code. But I, J, K is extremely common in all C programs. So we have our loop control variable. We have our portion of the for loop that initializes I to be 0. We could have initialized it before, but it does need to be initialized as part of the loop. We're going to loop as long as I is less than 25 in this case, and then we're going to add 1 to our variable I each time through the loop. Um, this code is doing something a little bit funny in that we haven't learned this about our printf. In printf calls, you can actually specify how many characters wide you want the printing of a variable to be. That's not always something we want to do unless it has to do with formatting a printout very accurately. So in this case, we can actually specify not a constant number of characters to print it out by. We can actually specify I want a variable number of width for printing something out. And if you do that percent star syntax, you then need to provide an integer for that value. This code's a little wacky in that it's saying enter in a character, so not an integer, although a short int here, but an ASCII character. And it's just going to print out that character 25 times. But each time it prints it out, it's going to make it wider. Not like stretched, like it's out of proportion, but in this case, it's just going to add blank spaces before it here. So favorite characters, J, obviously for everyone in this class. And we're printing J with just extra space as we do it. In this case, 0 is the first value, that's no extra space. 1 total character, that's also no extra space. Then 2 characters, then 3 characters, then 4 characters, etc. Why would you want to do this? Well, to illustrate for loops, but also sometimes you want to print something really precisely with the right amount of width to it, and you would use that syntax potentially to do that. There's actually quite a bit of flexibility with how we define our for loops. Um, each of the 3 components, they don't have to be I equals 0, I less than 25, I plus plus. The following code there on this slide is a valid for loop. It's just not recommended. You can initialize the variable via scanf if you wanted to. That's valid syntax. Anything that does something is valid for that first component for any of the 3 components. Be I not equals 234. That's not necessarily odd, but it's not that common. And I mod equals 1, 2, 3, 4, 6. Okay, it's hard to imagine what this code would intend to do, but it's valid. You can actually also skip the components entirely. For no initialization in the for loop, for I less than 255, and no increment in the for loop syntax itself, well, that becomes a while loop. It's fine. You can do it that way. That's not very common. You'll sometimes see code that does an infinite loop in this way. For nothing, while always, do nothing. That loop is always going to execute until someone explicitly breaks out of that loop. But I would just suggest that for your for loops, you should, or when you're choosing to use for loops, it should be when you have a straightforward, repeatable segment of code. Your for loops should look like this. And if they're looking like this, then for loop probably isn't the right choice anyway. This would be a very hard thing to track down and debug. So while you have that flexibility in C, I think this semester you won't have to use any of that flexibility in your C programs. And in general, you maybe want to shy away from that. What is very common is for these index variables for our for loops, it's very common that you're going to increase or decrease a variable by 1 each loop. May not be obvious why that's the case yet, but we'll see why when we talk about arrays and we index into arrays, we want to grab element 0, then element 1, then element 2, and that loop variable I becomes perfect for indexing into that array. So you don't take my word for it, but it is extremely common that we want to go up by 1 or down by 1 each time through the loop. There's 2 other operators in C that are really perfect for this. That's the increment operator and the decrement operator. So instead of I equals I plus 1 or even I plus equals 1, we instead could have just I plus plus. There's a big caveat here, and I just want you to be careful with it, and I think it'll just take experience to become careful with it, that there's 2 different versions of the plus plus or minus minus operator. There's prefix increment and postfix increment. You can use it by itself. You can just write C++, and that's a small joke here, and that will increment the value of C. You don't have to say C equals C++. In fact, that's a little complicated what that would actually do. You just write C++ that increments the value of C. You can actually use the incremented value as part of another assignment. So that syntax below, both of them are valid. D equals C plus plus is a so-called postfix increment. We'll assign the original value of C to variable D, then we'll increment C. As compared to prefix or prefix increment, where we'd increment or decrement the variable first, and then we'll do the assignment. D equals plus plus C. I guess I would say in code that I see, postfix is much more common than prefix, but sometimes you do want this. You never need to use it. It's just an optimization in terms of lines of code. You can always write C++, then use it and assign that value. But this fits it all into one line. It makes our for loop look a little bit cleaner. We're not writing I plus equals 1. We're writing I plus plus, and that's why you would see it in many of your for loops. It can be a little hard to debug challenges with prefix and postfix incrementing of values. So if we started off with a equals 3 and b equals 4, we do d equals a plus plus. A is 4 because we've done the increment here. B is also 4 because we haven't done anything with it yet. The value of d afterwards for the printout, I need to be clear here, is going to just be 3. We're going to grab the value of a and store it as d, and then we're going to print it out. For this next example here, we're doing the prefix increment, where first we increment b, and then we're going to store it as d. So a hasn't changed, a is still 4. B is now going to be 5, because we're incrementing b. And when we print out d, that's also going to be 5. The increment happens first before the assignment here, it happens afterwards here. If your code starts to look like this next example, you may want to rethink it. A plus plus, so a is now 5. Plus plus b, so afterwards b is going to be 6. But what is going to be the value when we print out, or when we have the stored value of d here? A plus plus times plus plus b. We're going to take the current value of a, take the next value of b, and multiply them together. So it's actually not going to be 5 times 6, it's going to be 4 times 6, it's going to be 24. We increment d again here, it should be 6. Nothing should change in that case. Now this final example is a little interesting. Eventually we know a is going to be incremented, b hasn't changed. We actually can't say anything by spec, at least, as to what the correct value of d is going to be. It's actually undefined by the C specification what happens when in a single assignment you use both the variable itself and a prefix increment of that variable. Did we grab 6 or 7 for the first A? We could try it and see what result we get, but you can't rely on that necessarily in your programs. It's undefined via the spec. Let's leave things here for right now. We're going to look at nested for loops as well as some programming examples. You're probably ready to go with the programming practice for learning Module 4, but we have one more video where I'll walk you through an example of using loops as well as using nested loops.